welcome to another video on my channel. This video will be the final introduction to calculus video before we continue with the final couple videos of the advanced geometry and trigonometry series. Hopefully you didn't forget about that. And then we will move on to the full-blown calculus series, which I think a lot of you have been waiting for quite some time already. So let's move on with the final video in the Intro to Calculus series, the epsilon delta definition of limit. Normally, I've been using language like approaches, goes towards, gets arbitrarily close. I don't think I said that. That sounds really nerdy. And tends toward. But there's a big problem with this. These aren't very precise at all, and rigorous proofs need precision. It's like saying a recipe needs some flour versus 2 cups flour, or saying my mouse needs to be small versus the specific dimensions that I would use my mouse. I'm no mouse expert, and no, I'm not talking about the real life mouse, I'm talking about the computer mouse, so I don't know the exact dimensions that I use mine on. If someone in the comments wanted to do it, my model is the Logitech G305. That's about it. That's the main problem with using all the limits, terms, and everything I've used so far. Now, why do we need precision? I already said rigorous proofs and more advanced mathematics requires what here it says unambiguous. Basically, it cannot be vague. It has to be very clear, on point, and detailed. And that's really about it for the advanced pure mathematics. But also, there's mathematicians like Cauchy and Weierstrass demanded rigor. The sections 1 and 2 over here are more of just historical context. If you want to know, if you want to research about that, you of course can. No one's stopping you, and it's actually quite interesting. There are channels which talk about the different mathematicians in the past. Veritasium is one. There is talks about a lot of mathematicians. And 3 Blue 1 Brown, 3B 1B. I'm sure a lot of people watching this channel have watched these 2 channels, but just in case any of the viewers haven't, there you go. Now, one final modern necessity is that computer algorithms need exact specifications. If I tell my computer, okay, perform 2 plus 2, then they will know what to do because I'm telling them to perform an operation and I'm telling them what the operation is. Versus if I say, perform some calculations. The computer doesn't know what calculations it could be. It could be 2 plus 2, it could be 4 plus 4, it could even be 800,753 times 17,853. So we need computer algorithms with exact specifications. Maybe there will be a time when they don't, but at least for the foreseeable future, they will need a lot of exact specifications, and that's what code does. There are two key questions in order to make this definition precise. How close is close enough, air quotes of course, for f of x to L, where L is the exact limit of f of x, and how close must x be to A, which is the value x is approaching towards, to guarantee this. Now, the insight is the answer to number 1 should determine the answer to number 2, and that's where the epsilon delta definition comes in handy. Think of it as a challenge game, and this is actually something I didn't really figure out before. When I was looking online and researching to make this presentation, I found this, and it's actually really interesting. I like the definition a lot, and it kind of is almost relatable, as there are a lot of people who play video games. Maybe not everyone who watches my channel, but a lot of the people I know do play video games. So let's say it's a challenge game where the challenger says make f of x within 0.01 of the limit L. And then you respond with a different value. This value is saying if x is within this much of A, in this case 0.005 of A, that means I can do it. Yes, I can do it. You just have to make sure that x is within this. And the challenger says again, alright, make it 0.0001 within that of L. And then you're like, alright, that's okay, but it has to be 0.00005 of A. That's the only condition I have, otherwise I'll be able to do it. The pattern is, no matter how small the challenger's tolerance, you can always find a suitable response, and you can always complete the challenge. Now let's get fancy and incorporate a second language. Epsilon and delta, if you didn't know, are Greek letters, which are in, of course, the Greek alphabet. Now, E, or epsilon, for me it just looks like E, represents how close f of x must be to L. It represents the challenger's demand. It's always positive and can be very, 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 very small. Now, delta, which kind of looks like a weird version of D, represents how close x must be in A to make sure that we can satisfy the challenge, or we can make sure that epsilon is this small. And it's also positive, and it depends on epsilon. Why these letters? Now, German mathematicians, it's from history, German mathematicians use epsilon for error, or the amount of variation within the actual limit, so it's almost like an error. And delta is for difference, basically how much different x must be to A to see and to figure out that how much error is allowed over there. So the process is saying, alright, we can have this much error, but then your response is, we can have, as long as you can make it this much difference, I'll be able to figure out and solve this challenge. Here we are, the formal definition that defines every limit. The definition is, for limit as x approaches A, f of x is equal to L, is if and only if for every epsilon is greater than 0, there exists a delta is greater than 0, such that if 0 is less than x minus A is less than delta, then f of x minus L, absolute value, is less than epsilon. Basically, of course, this is kind of the tolerance or the challenge game, which is the translation, which is saying no matter whatever value, no matter whatever error or tolerance or whatever you say you give me for this function, I can find the positive delta that keeping x within delta guarantees f of x stays within epsilon of L. So you're trying to find delta from epsilon given, and in the game theoretic view or the game view, we can say that as long as it's within this value, it can happen, because the question is to make sure that you can keep it within epsilon of L, but this is the formal definition and switches it around. So the game theory view is not 100% accurate, it conveys the concepts, but it's just the definition is a slightly different problem. Let's break down this definition in 4 parts. Part 1 is for every epsilon is greater than 0. That means it must work for all positive epsilon values. Now, it's of course the challenger's choice. The challenger gets to choose any epsilon is greater than 0. There are no exceptions, and that's what makes this definition so powerful and so demanding. The second part of breaking down this definition is there exists a delta greater than 0. Basically, we only need to find one delta that works in order for it to say that this works. Well, that's a lot of works in one sentence, but delta will usually depend on epsilon, and it's written as delta of epsilon. It's our response, and different epsilon values typically require different delta values. Now, if we go back up all the way to the formal definition, it's one value of delta, but also if you have x minus A is less than delta, that means that as of course it's within the limit, but also it's actually a small range, as there are multiple deltas that could work for a single function, but it only says that you have to find one. If this is part 3, and if the second last part is if 0 is less than x minus a, absolute value is less than x, this is all the x values we're considering, and that means it must be within delta distance of a. So really, if you almost look at it, it's almost like x is equal to delta plus a. And then of course we have to exclude x is equal to a itself, because if that's going to come in later in something called continuity, which I've covered. And why? The epsilon delta limit describes behavior near a point, not at the point, and that's what continuity does, near the point and at the point. But the function might not even be defined at x equals a, and if you remember one of my past videos, we call that a removable discontinuity if a limit exists but it's not defined. 4 in the final part is then f of x minus L is less than epsilon, the absolute value of course. Now this is our guarantee to the challenger that yes, this will happen no matter what, as long as the other conditions are met. F of x minus L is of course the distance between the two values is less than epsilon. The distance must be smaller than the challenge tolerance, and this is kind of the final part of our promise, is as long as we stay within delta of a, f of x stays within epsilon of L. A geometric interpretation or a visual representation, I couldn't find one online, but there might be there, or some people might even use AI to generate a diagram of this. The horizontal band is y values between L minus E and L plus E. I'm just going to say epsilon as E because I don't want to have to say epsilon a lot, because it's going to recur a lot of times during this video. So it's almost like a horizontal band. Of course, there's the y-axis, the x-axis. It's parallel to the x-axis. Both limits of the band are parallel to the x-axis, perpendicular to the y-axis. And that's one part of the equation. The second part is a vertical band, which is the vertical delta band, which is x values between a minus delta and a plus delta. Of course, we have to exclude x is equal to a. Now, what the requirement is, every x in the delta band must map to a y value in the epsilon band. Now, if it doesn't become true is if we have delta be too much, and that means it strays farther and farther from what's in epsilon. I'm not going to fully prove it, that can be an exercise on your own, and there are a lot of online resources. This video is more to give you an introduction and understand how it is used, because instead of just rigorously proving this definition, I know the point of this video was about rigor, but proving this would be its own entire video, and maybe during the calculus series I might do it. If you have those suggestions, please leave them down in the comments, because that's how I know what other videos to make specifically. I've done it before with our limits through graphs video. One of my commenters suggested that, and they really wanted it, that I wanted to show them the full definition of how it works through graphs, and that's what I did. So don't worry, your requests will be answered, you just have to make them known. So here is the general proof strategy. First, we have to say let epsilon is greater than 0 be given. Basically, let's accept the challenge. We have to work backwards from f of x minus L, absolute value is less than epsilon. Then we have to use absolute value properties and factor and simplify. Then we have to identify the constraints on x minus a. Basically, we need to find what bound we need. Then choose delta appropriately. Often it's actually delta is equal to epsilon divided by some constant k. Then write the forward direction, that if x minus a absolute value is less than delta, then f of x minus L is less than epsilon. And then just state that the limit exists, just a final fancy step that all math proofs need. Now the key insight is the scratch work, or what you're going to do with it, is goes backwards, but the technical final proof actually goes forwards in the steps shown below, or sorry, above. Basically, this proving techniques for linear functions. Now this is functions of the form f of x is equal to mx plus b, and what we're trying, and generally it's ma plus b, where you have a linear function. Now this slide and the next slide will actually be proving the values of delta to show that what it is within for a few special types of functions, linear functions and quadratic functions. And the second reason I'm actually not doing it is because to prove it for every major type of function, number one, it would take a long time, and number two, many of the techniques are in calculus, which we have not covered yet. So there are four main steps. If we have f of x minus L is of course less than epsilon, so we have to have mx plus b minus ma plus b, which is also less than epsilon, but also f of x is mx plus b and the limit is ma plus b. Then what you have to do is you have to factor, so it's m times x minus a plus b outside of the function absolute value plus m, and then times x minus a absolute value. That means we need this value to be less than epsilon. What they didn't miss is that b canceled out. Sometimes I forget when I'm doing these recordings. Sometimes nerves happen and everything. But yes, that's how the proof process works. And then, therefore, x minus a is less than e over m. And now we choose delta to be that x minus a is equal to e over m absolute value, and it kind of follows our conclusion from the previous slide, where it says often delta is sum e divided by k for some constant k. Now, why this function works is linear functions have a constant rate of change, so the relationship between input and output changes is predictable, so it's quite easy to solve. Now, one final special case is if m is equal to 0, then f of x is equal to b, it's constant, and anything works. It's always going to be that specific limit. Now, proof techniques for polynomial functions is a little more advanced and complicated. So for functions like f of x is x to the n or more complex polynomials, basically higher degree terms create more complex relationships. If you go on a program like Desmos and do x, it's pretty predictable. X squared even, it's pretty predictable. But then if we start to go even beyond like x cubed, x to the fourth, x to the fifth, they start to follow a structure, but the change is rapid and not very predictable. So the general strategy is we have to factor the difference. Often, especially with polynomials and linear, they factor very nicely. Then bound the extra terms. Use preliminary restrictions like delta is less than or equal to 1. Now combine the bounds to make sure we have x minus a as a factor for some constant c. And then delta is the minimum of 1 and e over that constant c. Basically, it ensures the bounds are preliminary restriction and the epsilon requirement. Now, here is an example structure for x squared minus 4 near x equals 2. So, what we have is x squared minus 4 is equal to x minus 2 times x plus 2. So if x minus 2 is less than 1, then x plus 2 must be less than 5. You can solve this algebraically. So basically, that means it must be x squared minus 4 must be less than 5x minus 2, which means delta is the minimum of 1 and e over 5. Where, of course, e over 5, since this is epsilon, since this is epsilon over here, and then if you have epsilon over 5 is x minus 2, and we can assume this is delta or one of the values since we have near x equals. Proof techniques for transcendental functions, so not polynomials, trigonometric, exponential, or logarithmic functions. And these functions actually don't factor as nicely as polynomials. Normally you have to use much more advanced topics like series expansions, different bounding ways, composition of functions, and these are normally using pre-established properties from calculus itself. So we are not going to do these proof techniques, but let me know in the comments if anytime in the future you want me to cover proof techniques for a few types of transcendental functions. Now, of course, there is a 4-step process. Basically, it's to use known inequalities and bounds. This makes it simpler. We can exploit continuity at specific points, and normally exploiting continuity involves expansions, often with derivatives and series, so this gets more complicated. And number 3 is use composition with simpler functions. This is actually very, very effective at any level, especially in just regular calculus. I know it's a limits video and we're talking about proving epsilon delta, but it's very useful for calculus. If you understand how to break expressions down into simpler parts, it will save you a lot of time. And then the final thing is series expansions, which is the most advanced, and normally this is also used for some of the other transcendental functions, especially Taylor series, which is a form of power series. So, of course, let me know down in the comments if you want me to do this, but for the time being, I won't unless some suggestions come or we are deep into the calculus series. These are a few patterns and mistakes. First of all, we have to always start at let epsilon is be greater than 0 be given, which is the first step in every proof. Normally, if you start in any other step, if it starts to go haywire, and then you can't really understand what is actually going on, your work just becomes a tumbled mess of variables and you have to restart. You'll get mad and you'll probably quit after that, and you will probably blame me for doing so, and I don't want that to happen. So we always have to start with this. Then let's work backwards. We need to figure out what epsilon should be. Then we need to use preliminary bounds to restrict it. So basically what we're saying is delta is less than or equal to 1, or any other value like 0.5, 10. Of course, it always depends on the function. So we have to take a minimum. That means delta is equal to minimum, where you have bound 1, bound 2, when multiple constraint exists, and then you'll be able to figure out the delta which works. So common mistakes are choosing delta too early, don't guess delta equals to e without analysis, ignoring the 0 is less than. Remember, we have to exclude x is equal to a. That is more of an advanced continuity topic. Of course, you have to be very careful of algebraic levels. At any level of math, algebraic errors are very common. Don't think just because you know calculus you can't make errors on algebra. It's happened to me a lot of times, and I get very frustrated when it happens, but thankfully it's become a little less now that I've been practicing more and paying more attention to exactly what work I've been doing. Then, backwards logic is don't assume what you're trying to prove, which kind of is like the circular reasoning from the squeeze theorem video. And of course, watch that. It gives me views. I can get monetized, but also I really wish that you learn everything, and learning is a very good thing. Not only will it prepare you for school, also it might help you even have a passion for something. And if you have a passion for something, you'll be able to work harder and smarter, and you'll just generally develop good character traits, which will help you in life. So, of course, on the bottom, we always have to have a checklist just to make sure that you got everything correct. This is basically a checklist you should do for any proof of any function. Always use a checklist, not this exact one, of course, but for any proofs of this form, you should use something very similar to it. So, we have to start with let epsilon is greater than 0, choose the delta, showed the implication works, and concluded with the limit statement. Now, many people will overlook the concluded with the limit statement. The reason you shouldn't do it is really a technical reason that formal math proofs, require you to conclude with the statement and require some sort of outline and different types of notation, and that's basically pretty complicated fancy stuff. But if you're just doing it at home, you don't really have to do it. It's kind of assumed. You can just revel in the satisfaction that you did something that you didn't really have to search up online for. Are a few applications where we're actually proving limit laws. Now, the limit laws, what I'm talking about is like the sum rule, product rule, subtraction rule, difference rule, quotient rule. We always have to add the fancy terms. And an important note is these aren't obvious. They require careful arguments, and I won't really show much of this. You can read it off of the screen, and it's actually quite interesting how epsilon delta is used to prove so many things and so many limits that even I've taken for granted for a very long time. I only learned the epsilon delta definition pretty recently. And now we'll cover the final thing, where is when limits don't exist. So to prove a limit exists, for every epsilon we need to find a delta, and to prove a limit doesn't exist, find one epsilon for which no delta works. Normally, the epsilon can be very, very small, as it forces the value of delta to be smaller, but of course every function is unique and different. A classic example is sine of 1 over x, as limit x approaches 0. Number 1, if we just direct substitute, limit 1 at sine of 1 over 0 is sine of infinity, and it oscillates very fast or infinitely often. So that's why, and proof strategy will choose a random epsilon, let's say 1 over 2, and using careful algebraic manipulation, show that for any delta is equal to 0, we cannot find x values for within delta of 0, where sine 1 over x is equal to 1, and sine 1 over x is equal to negative 1. And the conclusion is no single limit value works. Also, you can use the squeeze theorem for this if we bound it between negative 1 and 1. If we bound it between negative 1 and 1, and it shows that you don't actually have the limit, as the values are not the same as it approaches a certain value. So the conclusion is no single limit value works. And of course, there are many functions where limits don't exist. A few examples are step functions, oscillating functions, and functions with different left-right limit. Now, this is looking forward to all of calculus, which will begin in a couple of weeks. This is continuity, derivatives, advanced topics like conversions of sequences and series, and continuity, and integrals with the limits of Riemann sums. Now, calculus is actually quite rigor-based when you realize the epsilon delta definition, and there are entire branches of calculus and courses beyond calculus just based on proving many concepts in calculus and beyond. So this is really the power of precise definitions. Once we make concepts rigorous, we can build entire theories, we can build calculus, we can build linear algebra throughout all of these theories, as long as we have the base concepts be quite rigorous. Thank you so much for watching this video. I really appreciate it that all my viewers are over here, and I care about each of you deeply and hope you learn as much as you can from this channel. So please make sure to like, subscribe, and hit that notification button if you found this video good. And please comment down below if you have any suggestions. It really helps out a ton. So thank you so much. See you in the next one, and bye-bye.